Okay, all right. Thank you everyone for coming to my talk. I'm Micheal from Brevis, and I'm here to talk about Pico, a modular and performant zkVM built by us. But before I get into the nitty-gritty details of Pico's technical aspect, I just want to first give a quick review of what is zk verifiable computing. So this is like the simplest form of computation you can think of, where Alice wants to compute the result of a multiplication equation, and Alice spends some computation time to do it. And the interesting thing is that if Alice now wants to convince Bob the result of the computation is such and such, the only thing that Bob can do here is to actually run the computation again himself. So Bob spends the same time, a number of computation units and get the result. The interesting thing I want to highlight here is that the actual cost of computation between Alice and Bob may be different because their unit cost of computation might be different, even though they're computing the exact same thing. It might be the case Alice is spending only $10 on the computation, but Bob can be spending $1 million in this computation as well. So, now what is verifiable computing? Verifiable computing is a way to kind of solve this problem. That is like Alice, instead of just doing the computation itself, also generate something called a zk proof of the computation. The zk proof contains the input, the kind of computation you want to do, in this case multiplication, and the result. Now, it is actually additional computation units that need to be spent for Alice to actually generate the proof, but the nice thing is that once the proof is generated, Alice can send the proof to Bob or anyone who is now a verifier to verify the proof with a tiny amount of computation cost. And in this way, we effectively decouple the computation itself with the verification of the computation. And the good thing about verifiable computing in zk is that even if you have a different size of original computation, the cost you need to spend in verifying them stays constant. So this is a very important characteristics. You can utilize that to scale computation, migrate computation from one high unit cost location to one low unit cost location. So another benefit provided by zk verifiable computing is privacy. So in this particular case, Alice can generate a proof, and in the proof, you don't actually need to provide all the input. You can even hide some input inside, and Bob will be still able to verify the proof and say, okay, I agree, exists a number, but I don't even know the number, and the multiplication of the number with 122 equals this result. So there's also additional privacy benefit you can get using zk-based verifiable computing. Now, why am I talking about it, and why are we building Brevis as a platform that you can run arbitrary verifiable computing on top? Well, it is because it's actually quite important to power a lot of different computing paradigms and new use cases in blockchain, in AI, and even Web 2. So let's start with blockchain first. In blockchain, we all know blockchains are world computers, but blockchains are very, very slow world computers. It cannot run faster than a single server. It is extremely expensive. This is a kind of a computation environment that is really high unit cost. So you may say, wait, like we have layer 2, we have many scaling technologies, it cannot be that bad. Well, it actually is. So let me give you a very simple example. In every centralized exchanges, we all have this kind of a VIP trader program where if you traded a lot in the last month, you can get a trading fee discount in the next month. Well, if you look at all the DAXs today, until very recently, you don't have any single DAX that provides this feature. Well, why is that? Turns out that computing a user's historical trading volume on blockchain directly, no matter it's layer 2 or layer 1, is actually insanely expensive. Because you actually need to do a lot of heavy computation like Merkle inclusion proof to access users' historical data. So what Brevis can do in this kind of scenario is that it can offload some very heavy and complex computation on blockchain to an off-chain environment and use zk-based verifiable computing to generate the zk proof and submit the result back. You effectively migrate the computation away from this high unit cost environment to Brevis, which is a low unit cost environment, and then bring the proof back to use blockchain as only just a glue point of infinite amount of computation power available. So our partners are using Brevis today, across a range of different scenarios like a spot DAX, RWA asset, liquid risk taking, lending, perp DAX, active liquidity management, and many others. Among them, I would just want to give two very concrete examples. One is a feature we recently launched with PancakeSwap. So on PancakeSwap, they recently launched this new feature called Pancake Infinity, which is the hook-based DAX infrastructure. You can basically kind of change fee on the fly for different swap transactions. In this feature, Brevis power there are like 6 different pools to enable things like trading volume-based fee discount, where users themselves can generate trading volume proof periodically to qualify for certain VIP status, and then get ongoing trading fee discount, or generate proof of certain token holding as well. So as we can see, right now, these 6 pools now hold $30 million in liquidity, and importantly, it improves the bottom line for the exchange. It gets better revenue for the LPs because you create better market structure with this kind of a trading fee discount, a tier-based trading fee discount program, just like how you can do this with market makers on a centralized exchange. Another example I want to give is in the stable token RWA distribution challenge part. So let's say you launch a stable token, but what's next? You really need to distribute a stable token into different protocols to get adoption. Well, that becomes a pretty challenging question because like now, instead of just providing an LP-based staking contract and send out the reward, you really need to reward users' activity across a range of heterogeneous and very different protocols on very different chains. Well, how do you do that without actually creating a central point of failure, without creating a centralized business system, and make it fully transparent and fair that is verifiable for the community? Well, this is where Brevis comes in. And we built something called a continuous protocol incentivization protocol with Euro, which is a rising star in the stable token ecosystem, to power their entire incentive distribution by allowing users to generate zk proof of their token holding, of their stable token holding across a range of different protocols, and then directly claim reward through smart contract in a fully trust-free and fair way. So, we also recently are working with a major perpetual DAX to turn them into a zk-powered perp DAX. That is, you have a matching engine that just feels like Web2 perpetual swap DAX exchange, but behind the matching engine, you now have Brevis running as a proving engine to generate zk proof of the computation result, of the matching result. And instead of putting everything on chain, the proving engine will just selectively put users' balance states and the actual kind of the actual position and open interest is actually hidden using Brevis as a privacy-focused feature as well. So my prediction is that in 10 years, we're going to see 99% of computation for blockchain application going to happen off-chain and verified by zk proof and hopefully by Brevis. So, this is not only about blockchain. Verifiable computing have a wide range of application scenarios, even in AI. So today, let's say you're interacting with the AI black box and saying that, can you analyze this quarterly financial reports and tell me if I should buy the stock? It's the large language model today, and in the future, especially when it is becoming decentralized, is really just a black box for you. You input something and it spits something out. How can you tell if you're interacting with a very intelligent model or something that is quite retarded? Well, with something called zkML, it's also powered by Brevis, you can actually do this by generating proofs to say that, okay, I'm getting this result not from a crappy model, but from a model that is pre-committed and match the certain kind of a qualification benchmark tests. And there are so many other use cases in Web2 as well, but I don't have time to get into them today. Now, I talked about what Brevis have been doing and integrated with different dApps and what Brevis can do in the future, but what actually inside the magic box? Well, we're going to talk about that. So Brevis is actually 3 components: our zk coprocessor, the Pico zkVM, and the proving network. So in the middle of our stack is the Pico zkVM that allows you to really prove any kind of computation you want. It is a RISC-V ISA-based zkVM with a bunch of function-level precompiles binding to accelerate certain operation speed. And the first thing about Brevis is it is developer-friendly, right? So the first thing about Pico is that it makes the ZK development really friendly for developers. So comparing to directly write your own ZK circuit for, let's say, Fibonacci number, this is like how many lines you need to actually write. Writing the same kind of logic in Brevis, Pico zkVM only requires you to write this small amount of code. And the good thing about this small amount of code is that it's just a plain Rust. Because underlying is a generalized VM, you can really write anything on top. And Pico is also blazingly fast. It is very general, but it's also fast. We're the fastest zkVM on CPU, and just last week, we announced our GPU version, the first version of our GPU prover that allows you to actually accelerate the CPU prover by approximately 20 times. And we also launched a benchmark test with other GPU-supported provers. Right now, we only support production proving in one single 4090 GPU, but we have a clustering proving coming soon. So, like for example, we just this morning benchmarked our multi GPU proving, which is also giving some promising early results, and we're going to share with more about that in a month or so. So Pico right now is live on ETHProof, which is a great platform. You can look at performance of different zkVMs. And on the single GPU sector, we are achieving consistently highest performance among all the GPU provers available. So we talked about how Pico is very general and can be used in any kind of application use cases. But we all know that in computer systems, it's all about trade-off design, right? So like we have a extremely high generality for Pico VM as is, and many other zkVMs as well. But the problem about this is that you are actually sacrificing some level of performance, and in some cases, a pretty significant level of performances. What you can also do in ZK to build verifiable computing system is you can make a very specialized circuit that's very hard to write, very hard to use, and very hard to interact with. You have high performance, but it can almost just only do one thing. So what we want for Brevis as a whole platform, not just a single piece of technology, is to operate at the sweet spot of both high generality and high performance. Well, how do we do that? This is where the modularity of Pico really comes to the rescue, where we treat Pico zkVM just as a glue to glue many different kind of a computation that can be specialized together. And these specialized computation, we call them coprocessors. So on Pico, on top of this general architecture, we have built a very, very extendable and modular framework where you can plug in your enshrined application-level provers, application-level coprocessors, things like on-chain data coprocessor, zkML, that is focusing on AI, and many other different kind of coprocessors as well. So let me give you a very specific example. In blockchain space, a lot of use cases we see involves calculating and computing and access on historical on-chain, on-blockchain data, such as computing what is the user trading volume, for example, is to access users trading events in the past. So we actually built this on-chain ZK data coprocessor where you can generate ZKP for arbitrary computation on any historical data and use that directly in our zkVM. So from a developer point of view, they are just calling a packaged SDK API, and however underlying what happens is that the zkVM is yet again offload this kind of a application level computation to a specialized system where a result can be returned and utilized in the zkVM again. So this kind of architecture really offers some benefit, in the adoption and go-to-market for our platform. That is, like you can see, even with the GPU acceleration for certain use cases, it's still pretty slow. But with the ZK coprocessor powered performance, it can be 80 times faster. So this is not the only coprocessor we build. We also have the zkML coprocessor that is in development. We released some early result last year. It's called SPA-ZK, a GKR-based proving system that is entirely different from what we build our VM on top. And we also have a bridge kind of a coprocessors. Let's say if you want to use and prove consensus of different kind of blockchains, then you can use this kind of a coprocessor, plug that into your generalized zkVM programs. And we also are working with a lot of providers in the AI and data industry to actually enable computation on zkTLS data. So we are integrating many of these zkTLS solutions into Pico VM as our coprocessor as well. So there are actually a lot of different application use cases that I haven't got time to get into. And one very interesting one is that you can actually generate, for example, like today for AI, you really want to kind of collect not only just public domain data, but also private domain data from user directly. But the problem for many of the operators is that how can you attest and how can you verify the data provided by user is actually the authenticated data? Well, using Brevis and our zkTLS coprocessor, you can actually allow user to generate proof saying that, hey, look, this is actually my PayPal data. This is my kind of a purchase history. But I'm not going to tell you everything about my purchase. I'm actually going to generate a summary of my purchase behavior in the last month. Let's say, I basically spent this much on food, this much on entertainment, and so on and so forth. And then, you as a data collector can actually faithfully verify using ZK proof that the data user computed on is actually his raw PayPal data, and the computation result is actually correct. So this is also a very exciting use case that we have been building with our partners. So finally, I just want to touch on the Brevis Prover Net, which is coming soon. That will handle and undertake all the proving requests from our ecosystem projects, which is a decentralized network that anyone can participate in with arbitrary kind of hardware and software. Finally, this is my last slide. We just started our community building process as well. We really want to invite developers, community members to join our community and build verifiable computing future with us. This is our Twitter. You can scan it and follow it. I think I still have like 2 minutes for some questions.
Can you share like a little bit more technical details on how the Pico is like composed? What is the PIOP you use? What is the PCS you are using? Like a little bit maybe on those.
Yeah, so like this is actually a great question, right? So like Pico is is building the Plonky3 framework, but it's a modular. So one thing that I didn't mention is that it's not only modular in the sense of it support application coprocessors, application level coprocessor, but it's also modular in terms of like the proving system it actually uses. So in one configuration, with just one line of code change, we actually currently support Stark on M31, Circle Stark, and also Stark on Baby Bear and Polar Bear, Koala Bear as well. So like all these things are possible, and we actually think this kind of a low-level modularity is also very important for user to actually test what underlying proving system actually works best for their workload, and this is something that we are seeing for many of our partners as well. All right, I think my time is up. All right, thank you, everyone.